Hey everyone, our new topic today is hashing. Before we start to talk about hashing, remember a couple of lectures ago, it was a time that we still had face-to-face lecture, and at that time we talk about a data type called dynamic sets. And I say this is just a conceptual data type, and it can have a lot of different implementations. And the basic idea is for each of the elements, we have a key and a satellite data. So you can consider it as a collection of key and the data pairs. Okay, and for this kind of dynamic set, and we can do search, maximum, successor, predecessor, and we can modify that by doing insertions or deletions. So those are all the actions or behavior we want to support in a conceptual data set, conceptual data type called dynamic set. Okay, and well, if we want to implement a dynamic set using linked list, and of course it is doable. So if we want to find the minimum and the minimum, and if we are dealing with a unsorted linked list, and what we have to do is we have to visit all the values in the linked list one by one, right? How about we make it sorted? I'm talking about a sorted linked list. So, for example, if we are trying to do a sorted linked list like this, so we have the head, and then the head points to the lowest value, and then the lowest value will point to the next lowest value. So in this case, I'm keeping all the values sorted intentionally. Okay, so in this case, if we want to find the smallest value, and you can see, well, the head points to the smallest value, right? So in this case, to find the minimum, and we can do that in constant time. Okay, so minimum, we can do that in constant time. And how about the maximum? If we want to do the maximum, and which is the tail of the linked list. So in this case, we can't really do that. We have to visit all the nodes, start from the head, the first node, the second node, and all the way down until we visit the last node. And this will be an ON. So how can we do better? One of the trick we can do is, other than the head reference, we also have a tail reference. So this tail reference will give us the reference directly to the tail of the linked list. So now we can have the minimum, which is the head, we can have the maximum, which is the tail. So in this case, for both the maximum and the minimum, we can do that in the constant time. Okay, so let's see what is the next. Okay, so okay, the next one is a successor. So if we have a node, and how do we know the next node? And this is also easy, because if we know we are visiting one of the current node now. Okay, so how do we know the next node? And the next node will be just we follow the next reference, and then we will find the next node, and that is the successor, right? So for the successor, it can also be done in constant time, so that's good. And how about delete? So well, for the deletion, we are assuming that we have already done the search. We have already found the node we want to delete. And the next part, what is the time complexity for doing the delete? And well, if you remember what we have learned before, this is also a constant time. Because, well, if we want to delete 10, and then we want to skip 10 by using the tooth reference directly to the 13. So we want to update a reference like this. Okay, so we find the predecessor, and then the predecessor's next will point to 10's next. So we delete the 10. Well, and there's a important assumption that we are gonna say, well, given we have already done the search, we have already done the search to find the node we want to delete, and at the same time we have already find the predecessor. So the reason is we are going to use the predecessor to skip the node we want to delete. So assuming that we have already done the search, we have already find the node to delete and the predecessor, and then the deletion can be done in the O1 time as well. So what's the next? Okay. The next one is predecessor. So for the predecessor, here is a problem. So if we are staying with the current linked list, and then for the predecessor, we have to go through all the list again before we can find that. So for example, if we are trying to find the predecessor of the current node, which is 10, so the only way to do that is we have to start from the very beginning, and then we go through all the nodes before 10 before we can find the predecessor. So in this case, to find the predecessor of 10, it will be a ON. So the question is again, how do we do better? So in this case, remember there is a doubly linked list. So for the doubly linked list, we have the next reference, and we also have a previous reference. So for each of the node, it knows the successor and the predecessor. So for example, for the 13, 13 will know the predecessor is a 10. For the 10, it also knows the predecessor is the 2. So in this case, for each of the node, it knows the predecessor and the successor. So in this case, if we are holding the 10, for example, and then the predecessor can be done with the O1 time. So, okay, if we are staying with the current design, we are doing a sorted doubly linked list. And what you will see is for the maximum, minimum, successor, delete, and predecessor, they can all be done with O1 constant time. Okay? So the next thing, how about the search? If we want to search for a value, for example, if we want to search for 20 in my linked list, and I don't have a 20, but how do I do the search? I have to visit all the nodes one by one. So for the search, well, there's no easy way. It has to be a ON in this case. And the next one, how about insertion? So for the insertion, what you have to pay attention is we have to keep all the values sorted, right? So in this case, we have to find the right location for the value first before we can do the insertion. So in this case, we have to visit all the possible gaps in order to find the right gap for the new value. So for example, if we are inserting a 12, so 12, can we insert it here? Can we insert it here? No. Can we insert it here? 12 is not the right place. And how about here? So 10 is smaller than 12 and 13 is greater than 12. So this location will be the right location for 12. However, to do this kind of search to find the right location for the new value, this process will be the ON time. Okay, oops. Okay, here. Okay, so this is a quick review of the linked list. So if we are trying to make a linked list to implement the dynamic set, so this is a dynamic set, right? If we want to use the linked list to implement the dynamic set, and what the bad thing we can do is for the first 4 actions, and we can do O1, and for the remaining 2, search and the insertion, they have to be ON in this case. Okay, and the next one. How about we implement the dynamic set with the red-black tree? Okay, so for the red-black tree, it is a balanced binary search tree, right? So what is the maximum and the minimum? So if we have the root, and then if we always go left, go left, go left, we will find the minimum. If we always go right, go right, go right, and we will find the maximum. And Well, how many steps we are going to go? Either go left side or go to the right side. And you should remember that will be O log n, right? Because the height of the tree is O log n. So we only have to go from the root to all the way down to one side to the bottom, and then we find the maximum or the minimum. So for the max and min, they can be done with O log n time. And how about the successor? So successor and the predecessor, they can also be done with the O log n time. And for the deletion, well, I require you guys to read the textbook, and you should know this is also O log n time. And for the search, if you want to search in a red-black tree, and the red-black tree's height is O log n, so the search is also O log n. And for the insertion, we have done the insertion. So insertion, and after insertion, remember we also have to fix the tree. So this is also a O log n behavior. So for all those actions, if we are implementing the dynamic set with a red-black tree, and this is all the actions will be O log n. Okay, so why do we want to do a hashing? So for the hashing, actually we want to do, it can be considered as another implementation of the dynamic set. And here is another example. So if we are building a compiler, and in this compiler, so you can consider that we want to compile a programming language like Python. Say, well, in a programming language, and what you have to do is you have to maintain a a a list of all the defined variables. Say, for example, if I want to do a equals 10, I want to do a name equals Yang, and then I want to create a list called my list, and it equals some value here. Okay, so those are just the variables we defined, right? So in the compiler, it has to know all those variable names. So in the compiler, what it will maintain is a list of the variable names already defined in the program. So for example, it will know the name A, and then it will reference it to some of the memory space. And so in this memory space, and it holds the value 10. And for the name, it will refer to another of the memory space, and this might be a little bit larger because that is a string, and that string is Yang. Okay, and then for the my list, and it could be in another place, and since this is a list, and the memory space can be even larger because we are doing random memory accessing, so it's really no guarantee where can we find the 10 or the Yang or the list defined. However, as long as we are keeping a record of all the variable names we have already defined, and plus for each of the variable name we can take the reference to find the real value in the memory, and then we are maintaining a list of all the defined values, and by looking on the names and then take the reference, we will also find the value behind the variable name. Okay, so this is the concept of the references. This is the symbol table in a compiler. So for all the programming languages, they should have something similar, because for any programming language, they have to maintain a list of the defined variables. So when you are using a variable has not been defined, and so the compiler will give you an arrow saying you want to use a variable named X. However, this variable named X is not defined. So for this kind of symbol table, and sometimes we may also call that a dictionary, what we have to do is we want to do search, we want to do insertion, we want to do deletions. So, well, to do a search, for example, if I'm using another line of the code, say a equals a plus 2. Okay, so I'm just taking the value of a, we add 2 to the current value and then put it back to a, right? So in this case, when the compiler says the a here, well, it has to use the variable name a to find the real value behind the a. So the compiler will go to the symbol table, find the variable name a, and then go down to the memory space to find the value, which is 10. So we are trying to do a search in this case so that we can get the what is the value a behind the variable name a. Okay, let me give you another example. Say, for example, if we want to do a insertion, we are just adding one more value. Say, I say x equals true. So I'm just creating another variable name called x. In this case, I have to update the symbol table. So we have to add a new x here, and then I also have to create a memory space saying this is a true, right? So in this case, I'm adding one more entry or one more symbol into the symbol table. And another example, actually we kind of don't use that in Python, is, well, how about later I am done with using my list, and after that I want to claim to the Python compiler saying, hey, Python, now forget about the variable name called mylist because I don't need that variable name anymore, and you can also release the memory space. So what I'm trying to do is, okay, Python, forget about the variable name mylist, and you also forget about this memory. So this memory can be released in this case. So, well, usually in the old style programming languages like C, we have that. We can say, okay, forget about this variable name and also release the memory space. But in Python, usually we don't do that. Okay, anyhow, those are the a few examples that we want to do search, we want to do insertion, we want to do deletion in the symbol table. Okay, and another point is we usually don't really care about how those symbols are sorted or not. So if we have a symbol table starting from the A and end with Z, well, that's okay, but we don't really worry about whether it is sorted or not. But in addition, we want to make the search, the insertion, and the deletion done as fast as possible. So this is a new challenge. Well, we still want to do a dynamic set. However, we want this dynamic set to be able to do search, insertion, and deletion really fast as possible. And for the fast, I mean, if possible, I want to have all those three to be constant time. Okay, so I think this video is already long enough, and I will see you in the next video.